Good morning. We are going to begin today our lectures on the ME171, Modeling and Simulation of Mechatronic Systems, and Modeling and Simulation of Mechatronics and Control Systems. So in this, today we will look at the basics of what make up those systems, and we will also experience a computer simulation that each of you will be able to do. So, all right, let's just look at our first application of mechatronic systems. Here you have a situation where where you see a vehicle here, you see icing here, and you see a antenna here, a positioning antenna on the bottom. Let's talk about the first one. Everybody has one of these. You use a vehicle to come to school. This is one of the things that everybody uses. But nobody really thinks about the kind of systems or the kind of things that go on inside the vehicle to make it work. Then we just get in our car, turn our keys, crank the engine, starts, and then off we go. What I want you to reflect is a little bit on the situation here where we have the that action of starting the vehicle. You have a basic transformation, you may say, of a hydraulic system, of an electrical system into a mechanical system. That's what's happening when you start the engine and the engine begins turning. You transform electrical power into mechanical power. Now when the engine turns, you have the transformation of thermodynamic power or dynamic thermal systems into mechanical systems. You may recall that there's only a certain percentage of all that energy used in combustion that is used for the systems for producing electrical, for producing the motion. Okay, let's analyze this system here in the sense that if you have the car running, like I said, it's transformation of thermal energy into mechanical energy. But let's examine a little bit more in detail what happens when you drive. You take a step on the gas and the car shifts gears, right? Well, before that, you step on the brake and you put the car on reverse. Immediately when you do that, you felt a little jolt when the reverse gear goes in and the RPM of the car, of the engine goes down. What's happening internally? When you move the lever, you engage a hydraulic system inside the transmission that now connects the power of the engine to the drivetrain, and that's how you could drive in reverse. When you put it in neutral, it will accelerate. The engine will accelerate, and when you put in drive, you go forward. When you shift, that's where I was. When you shift, the hydraulic system again there's a transformation in there because of the different speeds that it has to go. So what happens is that you transform mechanical energy into hydraulic energy and vice versa. There is an interchange of these two. That's how you avoid having the clutch, because the clutch would be also a mechanical component where you actually engage the engine or you disengage the engine. But since most of you drive most of us, including me, drive an automatic, well, that's what's happening. Once you get to a certain speed, let's say you go on the freeway 65, put the cruise control in there, and the variation of this so-called steady state, you may say, is small, maybe 5 to plus or minus 5 miles an hour, before the control system tells, oh, accelerate a little or decelerate to maintain speed. And if you go up a hill and you have the cruise control, it's going to accelerate to maintain speed. But again, the transformation between thermal energy and mechanical energy is what drives this whole thing. So that's what I wanted to point out to you, that the whole operation of a vehicle is a combination of electrical systems, mechanical systems, hydraulic systems, thermal systems, the whole thing working together. If you're still not convinced, you get to a stop sign, what happens now? You're going to tap the brakes. When you tap the brakes, there is a transformation between the motion of the pedal into hydraulic pressure to all four wheels of your car. And that pressure of the hydraulic system is transforming to mechanical motion of the calipers that actually pressure the discs on the wheels to stop the car. So you see what I mean? This interaction between energy domains and between different systems is what actually drives the dynamic system. That's the world we live in. There was an interesting question that I read on one of the comments of students last semester. He says, I would like to know how this class fits into my life and into my career. Well, I think the little conversation I'm having with you is right to the point on the first question, because all we do is live with systems, and we live with mechatronic systems. We just don't talk about and we don't think about. You know, for a vehicle to work normally, for you to drive, there's so many systems that have to be working all at the same time. Think about it when you drive at night. Even the electrical system has a few circuits in there that they have to work together. When you signal to change lanes, another system kicks in. When you slow down, when you accelerate, when you stop, many systems have to work together, and they have to work right. One of those doesn't work right, your car doesn't work right, or could be a dangerous situation. Just to give you an idea, on the space shuttle, when the space shuttle takes off, there's about 2,000 systems that have to work in tandem together to make it work. Okay? So this is the extension of in answering the first question, you know, how does it fit in my life, is because everything to make it work is a combination of many systems. How does it fit in your career? Well, if you want to design something, you're gonna have to deal with the subject, because it's not enough that you design a nice part of a car or of a machine, and you analyze, you know, all the stresses and deformations that go on, and you size it really good, and you do the drawing so that the shop can make it. All this stuff is part of engineering. What happens in the end, what counts is whether this thing is going to work. And that's where we come in. So in answering the second question is, if you want to know whether a whole machine, a vehicle, a device, anything you design will work, you'll deal with this option. Okay, that's where we are. That's why this class is very important, not only to get you started on that thinking, but also is to give you some background on another course that comes later, which is the analysis of control systems. But first we need to deal with systems, and then later on with the controls that will drive this. Okay, so here are some examples on the slides. You can see a moving car, electric circuits, telescope. We have a positioning system in here. Think about this, the positioning system on an antenna, it has to go and position the antenna where the best reception is. To do that, you need some motors, and you need some controls to be able to tell the antenna exactly where to be. Think about what we're doing nowadays with the Mars rover, and to be able to do anything, it has to have the system and also control system. All right, I think it would be a good idea for us to go on to study the the process and the thinking process that go along with this. In here you see you have a you have the first box. In the first step, it talks about the physical system, and then you have the some schematic. It says schematic of the model. Schematic is so that we can understand it in our own words, in our own way, how you understand a system. Then you have your differential equations. This is the mathematical side of it. The transformation between reality into some mathematical representation that we can actually do something with. And then you have the block diagram method or the bond graph method that come to your rescue to be able to do and solve those equations. Okay? So in this method, in the block diagram method, you are going to be the one writing those equations, making sure that you describe well to a program like Simulink, and then getting the results analyzed. When you do the bond graph modeling method, you are relying more on the computer to give you the system, basic system for you, and give you those differential equations that otherwise you have to do by hand. I think there's no I am not here to say, oh, this method is better than that one, or vice versa. What happens over the years, I realized that some books deal only with this method, others deal only with this method. But the best thing for me to do for my students and to provide you the best service is to teach you both of those. And I devised the class to be able to do them in parallel. I think I want you to be aware of the differences between one or the other. And the reason that I teach both of those is because if you leave this class and you know both of these, you can talk to the rest of the world. Because there's people out there who do only block diagrams. Well, you talk to them in that way. But there's others who only do bond graphs. And there's some of us like me who do both of these. Okay? And I think it's in your best interest to do that. So if you once you are at this stage where you go from the mathematical representation to some tools to be able to solve it, you will come to a simulation language where both of these methods will converge. Like for example, MATLAB. MATLAB can take block diagrams, but also can the input to MATLAB could come from a bone graft model. And then you have the output in here. The outputs in forms of tables and graphs is what you need to be able to analyze the system in this way to get the results. I think it would be a good idea for us to look at, in general, at some simple system like this. You see, I think the effort that I made to make the color coding is going to help you. See here, this red color is identified with the inertia element, this element in here. Because this is a simple suspension system, here's the ground, and you have a spring and a damper and a mass. It's very simple oscillating system that has three different components. You see, this one in here, this mass, we are going to call the inertia element. And later on, we'll simplify our language. We will call it I element. Okay? Isn't it true that this one specifies a specific function? Spring does a very specific function in here. And we are going to call it a C element in there. See? And I put it for compliance element. I put this in with this color, and then I chose a different color for this resistive element, this damper. We're gonna call it the R element, and then in here would be the source, which would be the source of the motion or the disturbance, you may say, from the bottom of this would be from the ground. So that is the system. Now, one way of doing this is, if I am a step 2, right? I have the real system. Now I made a little sketch, and step 3 would entail getting these differential equations. In order to do that, we got to come back and review our E110 or basic dynamics class, where you will have you will write the differential equations of the system. Do you remember what Newton's law says? If you don't remember, let me remind you. In this case, the summation of the forces acting on a particle, acting on a body, is equal to the rate of change of momentum. That is Newton's law. Okay, so reading in different ways in here, summation of forces equals my double dot. These two dots are supposed to be on the y, so I apologize for that, but this is correct, m d squared y dt squared. So it's, or known, in other words, mass times acceleration. So if we look at the forces in here, the weight, of course, is one of them. If we move this mass a little bit up in the positive direction from the equilibrium position, you will see that we generate opposing forces. So k times y minus y of the ground, and the other would be the damping force, which would be b times the velocity of the mass minus the velocity of the ground. Now we could put these three forces into a summation as you see here, and come up with the differential equation that you see down here, which is the one that actually represents the dynamics of the system. My point here is that each one of these terms is associated with different elements. Like the inertia is associated with this y double dot, the resistive element is associated with y dot, and k is associated with y, and then we have the external force. So summation of the external forces equals to the rate of change of momentum. That is the basics for this whole thing. Okay, so what did we say in our steps? So we had the reality, we did the sketch, then we did a mathematical representation, which is where we are, and then we need to either use some method for solution, and that's what we can see next. What is the solution? What will determine the solution? You have several options in here. You can do an analytical solution, which would be almost like a prescription for the solution of simple systems, but you know, we don't live with simple systems, we live with normal systems, so that won't work. Then you have the block diagram or the bond graph method, or you write the program, or you use some simulation tools, or you use the Laplace transform using the frequency domain. Yesterday I was talking to a professor at the University of Texas, and he was asking me, he says, on the methods that you deal with, have you dealt with Mathematica? Is there anybody here who uses Mathematica? I heard this a wonderful program, and he had wonderful things to say. This is that the simulations for highly nonlinear systems are very well handled there in Mathematica, but here we will use of this listing here, we'll use the block diagram, we'll use the bond graph method. Writing a program, we would rather not to do that, but we would rather the computer does it for us. And then of course we will use the Laplace transform method, which is something that we will do by the end of the semester, by the end of this thick series of lectures. But basically the block diagram of that system, you have seen it you have it in front of you, and we can actually implement this block diagram. Now, block diagrams could be used with simulation languages that allow you to describe each block and assemble it to the point that it looks like the one we have in here. When I say look like, I don't necessarily mean graphics. I mean something like this. And here you see, this is the block diagram. And here we have written a little computer program that describes the block diagram. Well, this little computer program goes into a simulation language, and then we can actually get the results. But you heard me say a few moments ago, we would rather not do this kind of programming. But I think since we are learning and examining how things are done, we will test and try different things with a simple system. In that regards, you see that, for example, if you can follow this, you say MY double dot, right? That term is described here, see? That's what it means, MY double dot. MYDD stands for MY double dot. That's a way to represent this term. And to say, this term is the summation of these two, see? Of MG, and then we have b minus y dot minus y0 dot y dot is 1 over m, the integral of my double dot, and the initial condition. The difference here represents this blocking here, and y 0 is here, and then you integrate twice also to get this, and then y is this. So you see, it becomes a challenge to be creative to obtain these block diagrams. And so in this particular case, we need to look at this block diagram, either write a program or enter it in a program like Simulink. Now, what I want to show you is, right now we have equivalent representations of these systems. You have one system that has the block diagram, has the representation, this block diagram of the system, or you have this other representation called the bond graph. Now, how in the world do we interpret this? I think that it is important to analyze what's in here and what's in here. Hold on for a second.